Today, we're cracking open a really fascinating and honestly, a kind of mysterious mathematical tool, the beta function.
So let me just kick things off with a question for you. What if I told you there was one single mathematical function that secretly connects things like probability, factorials, for counting, and even helps solve some seriously nasty integrals? It sounds like it would have to be some kind of mathematical Swiss Army knife, right?
Well, that superstar function is real. It's part of an elite group known as special functions, and its name is the beta function. You can think of it as this hidden powerhouse, working behind the scenes in some of the most important areas of science and math.
All right, so here's our game plan. We're going to start with what makes this thing so special, its superpowers. Then we'll look at its actual blueprint, this core integral. After that, we'll uncover its most important relationship, the gamma function connection. Then we'll see it in action, and finally, we'll wrap it all up with why you should care.
So let's dive right into section 1, a function with superpowers.
So what's the big deal with this function? Well, first off, its day job is in the worlds of probability theory and combinatorics. That's the fancy math for counting things. It's built from a very specific integral, and it takes two inputs, we'll call them x and y. Now, one of its coolest features is that it's perfectly symmetrical. You can swap x and y and you get the exact same answer. And this is the really big one. It's a very close cousin to another celebrity in the math world, the gamma function. We're going to see just how important that family connection is in a bit.
Okay, that brings us right to its core design. Section 2, the blueprint, an integral.
And here it is. I know at first glance it looks a little intense. This is what's known as Euler's integral of the first kind. But let's just break it down. All we're really doing is calculating the area under a very specific curve between 0 and 1. That curve is defined by t to some power times 1 minus t to some other power. That's it. This formula, this is the DNA of the beta function.
And inside that formula, there's this really beautiful hidden property. See, b of xy is always equal to b of yx. It literally does not matter which order you plug your numbers in. The answer from that integral we just looked at will be exactly the same. This is a super fundamental property, and it makes the function incredibly consistent.
All right, let's move on because this is where we find the real secret sauce. Section 3, the gamma function connection.
I really can't overstate this. While that integral is what defines the beta function, its real-world power, its everyday usefulness, all of that comes from this deep relationship it has with the gamma function. This connection is what unlocks everything.
And here it is. This is the formula that completely changes the game. It says you can calculate the beta function without doing that complicated integral at all. Instead, just take the gamma of x, multiply it by the gamma of y, and then divide the whole thing by the gamma of x plus y. It's a massive shortcut that makes the beta function so much easier to actually use.
Okay, so we've got the key. Now let's see what doors it can open. On to section 4, putting the function to work.
So one of its biggest jobs is in statistics, where it forms the foundation of something called the beta distribution. Now, take a close look at that formula. The top part, that should look really familiar. It's the exact same piece from inside the beta integral. And what's on the bottom? The beta function itself.
So what does this distribution do? Well, it's perfect for modeling things that are proportions or percentages. Anything that has to have a value between 0 and 1. Think batting averages, voter preferences, that kind of stuff. It's a huge deal in Bayesian statistics. Now, those alpha and beta parameters, they let you control the shape of the probability curve. And the beta function's role? It's the normalization constant. That's just a fancy way of saying it scales the whole curve perfectly so that the total probability underneath it adds up to exactly 1, which, of course, it has to.
Next up, let's see how this function builds a bridge to a completely different field, combinatorics, the art of counting.
So check this out. When you plug in whole numbers, the beta function has this amazing direct link to factorials. As you can see from the table, you can calculate the result just using factorials. Now this is really cool because it creates this elegant connection between the smooth, continuous world of calculus and integrals and the discrete, step-by-step world of counting things.
But wait, there's more. The function also happens to be a secret weapon for anyone who has to solve really complex integrals.
Here's how it works. You can take that original integral definition, make a really clever substitution, setting t equal to sine squared theta,
and it magically transforms into this super useful trigonometric form. This lets us solve a whole bunch of integrals with sines and cosines that would otherwise be an absolute nightmare to figure out.
Okay, let's bring this all together in our final section, why the beta function matters.
So, what's the bottom line here? The beta function is this incredibly versatile tool. Yeah, it starts out as a simple integral, but its real power, its true potential, gets unlocked by that deep connection to the gamma function. That relationship makes it the backbone of the beta distribution, it gives us that neat bridge to counting things with factorials, and it's a clever trick for solving tough integrals. It really is a mathematical multi-tool.
And that kind of leaves us with one last thing to think about. The beta function is just one of these special functions. So it makes you wonder, right? What other hidden mathematical engines are out there quietly working behind the scenes, shaping the science and technology we use every single day?